So this is 2.4 complex numbers, starting out with number sets. A complex number has a real part and an imaginary part, a plus bi. If we're looking at real, we have rational and irrational numbers. Irrational numbers would be something like the square root of 7, maybe the square root of 2. Rational numbers are anything that can be written as n over m. So anything that can be written like that is a rational number. It includes fractions. It includes whole numbers like 2. It includes negative numbers. And it would include square roots that come out as perfect squares like the square root of 49. It also includes rational numbers include repeating decimals and terminating decimals. So there's a lot more in the rational category than irrational. Now, within irrational, we have what's called transcendental numbers. Transcendental numbers are not algebraic. So a good example of a transcendental number would be like pi or e. Integers are numbers that are not fractions, not decimals. So 1, 2, 3 going up, and 0 is an integer, as well as -1, -2, oh goodness, -3, ... Could kind of fix that. All right, so -1, -2, -3, and everything smaller. Whole numbers, I think of a donut hole. So a whole number starts with 0. 0 represents the donut hole. It's round. That's how I remember it. And then it's going to be integers. So 1, 2, 3, 4, and so forth. Positive integers, though. Natural numbers would be how you naturally start to count. You always naturally start to count with the number 1, and then you would go 2, 3, 4, and so forth. Imaginary numbers, you're looking at maybe the square root of -2 or the square root of -4. So numbers that are imaginary, like the square root of -4, we would write as 2i. That negative is the I for imaginary. So let's go ahead and continue this with looking at the powers of I. So if we start to talk about the powers of I, if we have I to the 0 power, anything to the 0 power is always 1. And if we have I to the first power, I represents the square root of a -1. And the square root of a -1 is what we're going to refer to as I. If we have I squared, let me come back with my pen. So if we have I squared, if we take I, which is the square root of -1, and we times it by the square root of -1, this would be I times I, which is equal to I squared. That is going to give us just -1. So I squared is equal to -1. This is something that you're going to use often in math. You're also going to use it often like on your ACT, SATs. We see I squared a lot. So this is one I'm going to highlight in green that you really need to know. I squared is always equal to -1. Okay, so if we were to look at I cubed, well, I cubed is the same thing as I squared times I. And we know that I squared is equal to -1. So this would be -1 times I, which is equal to -I. So what's interesting is I have I to the 0 is 1, I to the first is I to the second is -1, and I cubed is -I. And now what we're going to see is this same pattern is going to keep repeating over and over and over. So I to the fourth is the same thing as I squared times I squared. Well, I squared, remember, was equal to -1, and -1 times -1 is equal to 1. Do you notice, I'm going to draw a line here because we're going to see the pattern repeating. Notice I to the 0 is also 1. So let's do I to the 5th. I to the 5th, we could say is I squared times I cubed. We know I squared is -1, and we know I cubed is -I. And -1 times -I is simply going to be I. And you see the pattern? I to the 0 is 1, I to the 1st is I, and the pattern has repeated, 1 and I. So because of this pattern, I think I to the 6th should give me -1, repeating that pattern. Well, let's see what happens. Let's write it as I to the 3rd times I. Let's see, I to the 3rd. So, and I don't know why I wrote -I. Erase, 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 erase. Try again. All right, so I to the 3rd times I to the 3rd. Well, I to the 3rd is equal to -I. So this would be -I times -I. And that's going to give us I squared, and I squared is equal to -1. So again, I just want you guys to recognize this pattern that I went 1, and then I went I, and then I went -1, and then up here is 1, I, -1. So therefore, I to the 7th should be -I. And just to prove that, we would have I to the 3rd times I to the, do we want to do I to the 4th is 1? Why not? So I to the 3rd is -I times I to the 4th is 1, which is equal to -I. And do you notice here? 1I, -1, -I. Look at the pattern. 1I, -1, -I. So this same pattern repeats every 4. So what that means is I can take something like I to the 72nd power. And what you want to do is you want to take 72 and divide it by 4, because we have this repeating pattern in 4s. So 4 goes into 7 once, and 4 goes into 32 18, and it goes in evenly. So because there's no remainder, all right, because the remainder is 0, then the I to the 0 is going to equal 1. I to the 72 is also going to equal 1, because you're looking at the remainder. So the remainder of 0 is 1. The remainder of 1 is I. Remainder of 2 is -1. A remainder of 3 is -I. And then you would repeat remainder of 4, remainder of 5, remainder of 6, remainder of 7. And you get that same pattern. So you're looking at the remainders after you divide by 4. So if we have 73, that's just 1 larger than 72. So what's going to happen is we're going to have that remainder. So 4 goes into 7 again. I meant to write 73 here, guys. So 4 goes into 7 one time again. And then this is 3. And now I bring down a 3 and I go in 8 times, which is 32. And you can see that I have 1 remainder. So 18, it goes in even, and then I have a remainder 1. So you come over here to this repeating pattern, and now instead of the remainder being 0, the remainder is 1, which means what is I to the 73rd power equal? I. Well, what does I to the 74th power equal? That would be -1. Go to the next number. What does I to the 75th power equal? That would equal -I. And then we would just keep repeating the pattern. So it's super cool. Divide by 4, look at the remainder. ACT loves these, so this might be something that you'd want to remember for the ACT. Let's do 146. Let's divide it by 4 and let's evaluate the remainder. So 4 goes into 14 3 times. That's 12. And I get a 2, bring down the 6. 4 goes into 26 6 times, and that's 24. And you can see that my remainder is remainder 2. So if I come over here, here's remainder 0, here's remainder 1, and here's remainder 2. So what does I to the 146 power equal? The same as I squared, which is -1. Now what we're going to do is investigate what happens when we add and subtract and multiply. So let's look at this first one is a subtraction problem. A is subtraction, while B, there's no add or subtract in the middle, so it's multiplication. Something to keep in mind, I squared is always going to be replaced with a -1. So that's important to keep in mind on everything that you do. Now this subtraction is going to have to subtract through the parentheses, which gives me a -2 and a positive 4i. Now because I'm just adding, all we're going to do is combine like terms. So we're going to put the 3 and the -2 together, and then we're going to add the 7i and the plus 4i together. And this is going to be what we call a complex number because we will have a real part and an imaginary part. So 3 plus -2 is 1. That's the real part. 7i plus 4i is plus 11i. And that's the imaginary part. So standard form for complex numbers is A plus BI. Pretty good. So there is my solution. All right, the next problem is multiplication. And since it's a binomial times a binomial, we're going to use the distributive property, which is FOIL. So first times first is 6. 3 times 2 is 6. Outer is 3 times -4i is -12i. Inner, so 7i times 2 is plus 14i. And then L is last times last. A 7i times a -4i is a -28i squared. I times I is I squared. Now, the I squared is going to get replaced with a -1. So now let's just combine like terms and we'll have our answer. So this is 6, and a negative times a negative is a positive. So I'm going to be doing 6 plus 28. That's the real part, plus -12i plus 14i for the imaginary part. So my final answer is 34 plus 2i, and that is a complex number. I will highlight the correct answer. There we go. Example 2a is the same thing with just a little bit more difficulty. So if you're up for the challenge, stop this video and try it by yourself and then check your answer and see if you were right. So here I am. I'm going to go FOIL again. First times first. Oh, by the way, did you guys notice my guy here? Here's his happy face. Look at this. I can make 2 eyes. There's his happy face. Here's his smile. I can give him some hair. Here's his ears. There's a tongue if I want to draw his tongue. All right, so FOIL, here we go. First times first. So that gives me the square root of -3, and we're going to just leave it. We're going to rewrite that as the square root of 3i. So that negative underneath comes out as I. And then I'm multiplying that by 3. So that's first times first. Then I would do outer. So outsides is going to give me a 4. So this would be plus 4. I have the square root of 3. I have that negative coming out as an I. but then I also have this I, and so that's going to be I squared. Then I'm going to do inner, so that's plus 6I, and then last times last. So 2 times 4 is 8, and I times I is I squared. And that I squared is going to get replaced with 8 times -1 instead. All right? Okay, so now what we're going to do is just simplify a little bit, combine some like terms. So I squared here is also a -1. So we're going to take the real part and put it together, and then the imaginary part and put it together. So the real part, 4√3 negative is a real part, so -4√3. And then this 8 is real and it's negative, so this would be subtract 8. So there's my real part. And now I'm going to do my imaginary part. So my imaginary part is 3√3i. So 3√3i plus 6i. Okay, and then what you can do is you could just factor this I out so that you have a plus bi. So the a is going to be -4√3 subtract 8 plus, and then you've got 3√3 plus 6i. And you can just pull that I out behind. And that's in the form. Here's your a plus bi. All right, so let's go to b. You've got 3 of those. So this equals 2 subtract I times 2 subtract I times 2 subtract I. So you can take 2 of them and do FOIL. So we can go ahead and FOIL first, outer, inner, last. Here's my guy. So we'll do that first, and then we can multiply that answer to the 2 subtract I. So I recommend stopping the video, try it on your own, because I think that you'll really be able to do it and then compare answers. All right, so I'll go ahead and do it. 2 times 2 is 4. And then outer is -2i and inner is -2i. So that's -4i. And then last times last, a negative times a negative is a positive. And then I times I is I squared. And then I squared is going to get replaced with a -1. So now I have 4 subtract 1, which happens to be 3. So this would be 3 subtract 4i. And I'm going to multiply 3 subtract 4i to 2 subtract I. And I'm going to do the same thing again. First, outer, inner, last. Sounds good. All right, so first is 6. Outer and inner, I'm going to do all in one sweep. So -3i and -8i is -7i. No, 8, 9, 10, 11, -11i. I was thinking that when after I said it. All right, fix. All right, -11i. And then last times last is going to be positive. The negative times a negative is a positive. You've got a 4, and then you've got an I squared. And then cross that I squared out. It's going to be 4 times -1, which is -4. So when I combine like terms, I've got a 6 and a -4, which is a 2. So my final answer, I'll put it up over here, is 2 subtract 11i. And check me on that, but that's what I'm getting. 2 subtract 11i. So a complex conjugate is, we know a conjugate is a plus b, a minus b. A complex conjugate is simply a plus bi and a minus bi. So a lot of times you see this z standing for complex, and we've got a complex conjugate. So the first thing that they want us to do is multiply 3 subtract 4i by its conjugate. So you have 3 subtract 4i. Its complex conjugate is 3 plus 4i. You're going to do FOIL, first, outer, inner, last. When you're multiplying conjugates, outer inners always cancel. So you would do first times first is 9, and outside insides, I don't even write them down because I have a 12i and a negative 12i, they're gone. And that always happens with conjugates. Outside, insides cancel. And then last times last. So a negative 4 times 4 is a negative 16. I times I is I squared. So please remember, I times I equals I squared because you're multiplying. And then always remember that I squared is equal to a negative 1. So if you can remember those two things, you're golden. And then you're going to take the I squared, you're going to replace it with negative 1. And this is always multiplication. So this is a negative 16 times a negative 1, which is a positive 16. So now we have 9 plus 16, and that conjugate is going to give us 25. And there's our answer. Multiplying conjugates got rid of the imaginaries. Okay, so this next one, we're going to find x and y. All right, example 3b is probably a little bit new to a lot of you, but you're just going to use your same algebra skills. We're going to start by multiplying. So we're going to take, let me get my pen up and going. We're going to take first times first. So 2 times x is 2x. We're going to do outer, which is minus 2i. We're going to do inner, which is plus 3ix. And then last times last is a negative 3, and I times I is I squared. And again, I squared means multiply by a negative 1. That's going to equal 13, which is the real part, plus yi, which is the imaginary part. Now, we are supposed to figure out what x and y are. So that's what we're trying to do. So we're going to clean this up over here a little bit. I am going to do a negative 3 times a negative 1 is a positive 3. So I'm going to take the 2x plus 3. I'm going to call that my real part. So I've kind of grouped together my real part. And then I have plus, and now I'm going to group together my imaginary part. And my imaginary part is the negative 2i plus 3ix. So anything with i's grouped together. And that's going to equal my real part, which is 13, plus my imaginary part, which is y plus I. Now, because I have an equal sign, then what I can do is I can take the real part and set it equal to 13, and I can take the imaginary part and set it equal to yi. So let's start with the real part. So the real part would be 2x plus 3 is equal to 13. And all we're going to do is solve for x. So you would subtract 3 over. So 2x is equal to 10. And so x is equal to 5. So I've already solved for x, and now I'm ready to solve for y. So let's go ahead and take the imaginary part, which is the negative 2i plus 3ix, and put it equal to yi. Now the cool thing is you have i's on all of these. So the i's are basically going to all cancel, and this is why. Technically, you could factor out the I, and you have negative 2 plus 3x is equal to yi. And then you just divide the I out of the problem. So that's why there's no more i's. Now I have negative 2 plus 3, and I know what x is. X was equal to 5. So I'll go ahead and substitute in x. And now, ta-da, I can solve for y. So now I have 15 subtract 2, which is 13. So y is equal to 13. And I just figured out what both x and y are. X is 5 and y is 13. So example 4, we want to get the i's out of the denominator. So you notice there's an I in the denominator. Well, you should recall rationalizing the denominator means that we don't have any square roots in the bottom. Well, what does I stand for? I stands for the square root of a -1. So you don't want i's in the denominator. So what we're going to do is get rid of that I in the denominator by multiplying the top and bottom by the conjugate. So we would take the conjugate of 1 plus 2i is 1 subtract 2i. And then we would multiply the top by 1 subtract 2i. Now this is going to take a little bit of work to simplify, but when we're done, we should have no i's in the denominator, and that's how we're simplifying this. So let's start with the denominator. First times first is 1. Outside insides cancel because it's conjugates. And then look at this. 2 times -2 is -4, and I times I is I squared, which is -1. And so you can see I got rid of all the i's in the denominator, which is what I was trying to do. Now with the numerator, it's just a whole bunch of multiplying. So you could stop the video, multiply it out, and then check your answer. I'm going to start with just multiplying these first two binomials. So starting with multiplying those, we've got 2 times 4 is 8. So I'm going to write 8 up here. And then outside is -4i. And let's see, -4i plus 4i. Outside insides happen to cancel on that, even though they're not conjugates. And then last times last is subtract 2i squared. Now subtract 2i squared means subtract 2 times a -1. All right, from there, let's go ahead and 8 minus a -2 times -1 is really going to be 8 plus 2, which is 10. So now I have 10 times 1 subtract 2i over, and my denominator, remember, oh, I wrote it down here, sorry, down here, up here, is going to be 1 plus 4, which happens to be 5. So before you go ahead and distribute anything, how about dividing first? So 5 goes into 10 2 times, and now my final answer is going to be 2 times 1 and 2 times -2i, which is 2 subtract 4i. Ta-da! Example 5, if you guys remember, determinant is b squared minus 4ac. And so this, I checked and I couldn't factor it. So let's think about quadratic formula. Let's go with the determinant first. So 2 squared is 4. Subtract 4 times 5 times 1. And this is 4 subtract 20, which is -16. And since your determinant is a negative, we're going to have 2 imaginary solutions. And this is why we're getting complex solutions. So let's go ahead and use the quadratic formula. A is 5, B is 2, and C is 1. And let's plug it in and see what our 2 solutions are going to be. So X equals the opposite of B, -2, plus or minus the square root b squared minus 4ac. By the way, I already did b squared minus 4ac. It's -16 all over 2a, and a happens to be 5. All right, so simplifying, I have a -2 plus or minus, well, I know what the square root of -16 is. The square root of 16 is 4. The negative underneath is what makes it imaginary, over 10. Now, you can do this little trick where you draw a triangle, and if all the corners of the triangle can be reduced, then you can reduce. So sure enough, I have 2 goes into 10, 5. 2 goes into 4, 2. And 2 goes into -2, -1 time. Final answer, drum roll, -1 plus or minus 2i all over 5. Ta-da! Now, I do want to mention, while this is one way to write the answer, in standard form, which is a plus bi, you would break this up. So you would do -1/5 is -1/5 plus or minus 2/5 I, and that's in the form of a plus bi. So I try really hard to keep these videos 30 minutes and under. I sort of kind of did that, but this is everything you need to know for imaginary numbers. Stop, stop, stop.